Microphone on. See. Green light, mouse. Right.
All right, this is like third talk by Murnane, and she's actually talking about today. I'm very excited to hear about the using this like state-of-art high harmonics to understand the electron interaction and dynamic, many-body dynamics. So here she is.
Thanks so much, Murnane. Good to see everyone again, and thank goodness it's cooler. Yep. So as Murnane said, I talked about how to generate very fast bursts of shortwave and light, and how to use them, for static imaging of materials. Then Brendan talked about using them to try to understand phonon dynamics. And now finally, I'm going to talk about the topic of this summer school, which is, understanding body electrons. This is very much a work in progress. Whenever one has a new way to look at a material, it takes a while to address, well, what do you want to measure and how do you measure it well? And in our field, this is something the chemists, material scientists, and the condensed matter, the quantum scientists have struggled with. And of course, because you can't make any progress if you don't have synthesis, measurement, theory, and then a sort of a feedback loop. Progress can seem slow, but when you look over a decade or two, we've come a very long way in our ability and our understanding of what the properties of different materials. I had illusions of also talking about magnetism and spin dynamics, but I don't think you would have enjoyed that too much, because you might as well just cover one topic well, and it also reinforces what Dan Dessau will talk about for the probing quantum materials. So, as I said, we looked at some static properties in the first lecture, and then Brendan talked about the transport properties. And of course, there's very practical things that we can do, looking at the magnetic state, looking at electric field interfaces, but to fit better with the topic of this summer school, I'm not going to talk about that, and instead talk about timescales, what we can measure on the fastest timescale, and does it have anything that anybody outside the community might care about. And this was something that, it was a misunderstanding that our community sort of fell into, because for a long time, when I was your age, which was a long time ago, I was in graduate school in the 80s, we started to be able to make very short pulses in the few femtosecond range. And prior to that, as people were able to reduce the pulse duration of lasers from nanoseconds to picoseconds to femtoseconds, in every case, there was a new couple dynamic that one could look at. So, for example, you went from being able to use, shutters, camera shutters, which can, ease the motion of a speeding bullet. But once you go down to a picosecond, then you can start seeing the influence of coherent phonons, of coupling between different vibrational states. So the chemists had a field day looking at many of these processes, and so did the material scientists. And then as you go below a picosecond to a femtosecond, then only electrons can do anything in a femtosecond. So if the spin is on the charge, it's coupled to the charge, then you can see, for example, which I'm not going to talk about, you can see that if you excite an electron, you can also hybridize the spin polarization, so you can transfer spin polarization. And I'll talk about, well, what intrinsic properties can you measure, in the attosecond regime? But then I'll come back and go back up to a femtosecond, because if you're looking at any coupled phenomena that's coupled to the phonons, then you're talking about things above a femtosecond or even above 20 femtoseconds, because the lattice can't do anything in a time scale. The fastest phonon frequencies are on order of 100 femtoseconds. So our community sort of got in a race to make the shortest pulses, but and this is just my opinion. So, feel free to read the literature and conclude otherwise. In my opinion, the really interesting phenomena are the things where electrons are talking to phonons or talking to other many-body excitations. But still, it's interesting to ask, well, how do we measure, attosecond processes? Now, one thing sort of to reinforce that point, it's not just simply making a pulse shorter. Because if you ask, with what bandwidth do you need to support a certain pulse duration, we can use the uncertainty principle. And in our field, we often use it in the electron volt femtosecond sort of representation. So if you take your bandwidth in electron volts, multiply it by your full width at half maximum pulse duration in femtoseconds, you get 1. So that means for a 10 femtosecond pulse, what bandwidth, what coherent? It's Friday morning.
0.1.
0.1. 100 millielectron volts that is still on order of the bandwidth in a particular band in the electronic structure of a solid. All right? Have some hope, or a particular orbital, you have some hope of being able to correlate the dynamics with a certain transition or a certain, band. Now, what happens if I ask the same question for an attosecond pulse? What bandwidth are you going to need to make us a 1 attosecond pulse? A kilowatt, exactly, a kV, a keV. And good luck to you if you're going to make, you might be able to measure a band specific thing, but you have to be really careful that you understand the transitions. All right. So that's something that, so immediately that you have to be very careful about how you make measurements, or else you'll just blur a lot of things together. Then you ask, well, what could you look at? What is doing anything below a femtosecond in a material? So of course, if you have sort of a Mott-like interactions where the electron interactions are dictating the material's property, maybe you could see something there. On a organic photovoltaic or something like that, you could definitely have a photon coming in, a visible photon coming in, and charge transfer can happen. Those processes can be very fast, maybe on order of a femtosecond or so. Then if you think about optically excited electrons, before the electrons scatter to make a hot Fermi-Dirac distribution, that certainly can have a non-thermal distribution, because you're just taking electrons from occupied bands and sticking them somewhere. Instantaneously, that distribution will depend on the color you use. It'll depend on the transition probability. Right? So you could definitely see some of that. So that's electron screening, scattering, momentum and energy redistribution in materials. You could look at that. Certainly, if you look at X-ray induced processes, you can have very fast dynamics. If you stick an electron in a very highly excited state, that lifetime is very short. So you could look at that. And then if you use light fields to push electrons around, there we're able to do and make pulses that are even shorter than an attosecond. It's theory, it's a zeptosecond waveform. But I would argue that, this is, while it's intellectually interesting, it's not relevant to anything, like a materials function. But certainly you can measure it. Okay, so then, but even those processes that I'm talking about here, all of these depend on the electronic band one is in. So if you really want to measure an intrinsic property in a material, you have to try to figure out how to do that to probe individual bands and then figure out what the scattering or screening is. So it's not going to be because your bandwidth is too broad and the transitions aren't specific enough. But you can do it. It just, it took our field a while to figure out how. And this is the thing we talked about a lot on Monday. So, you know, how do you think about using it? Now, we can make these coherent supercontinua that are really correspond to a single recollision of the electron with the atom. And that single recollision then gives, it's a coherent bremsstrahlung. So you get a chirped attosecond pulse. And these are great for capturing events that last between 1 and 10 femtoseconds. This is because the bandwidth is broad. You can certainly send it through a material and probe the chemical shift or the magnetic or other signals. So it's well suited for transient absorption spectroscopies. And while they can probe transitions, you have to be very careful about how you do it. And the surprising thing is that this sort of pulse train, where these bursts emerge every half cycle of the laser. So with the Ti-sapphire laser, the spacing here, so this is the laser field in red, the X-ray bursts are in blue. And if you use a Ti-sapphire laser, the time difference between these two bursts is about 1 1/4 femtosecond. And it turns out if you're measuring very fast dynamics that are in the few attosecond regime, then it turns out this waveform is better to use because this corresponds to very narrow line widths. These individual harmonics can probe transitions from specific states to specific states. And if your dynamics are over very quickly, it doesn't really matter which pulse you use to probe the electron dynamics. So let me see if I can give you an example of that, how you get band specificity and still get to measure attosecond lifetime. Yes, Minion. Sure.
This has a, like the train length of about like, tens of the femtosecond.
Yep. Yeah, it can be 80 in fact. Yeah, it can be, this can be very long. And I talked a little phase matching, and that if you use a mid-IR laser, you automatically get phase matching. So you only make one isolated pulse. If you use a Ti-sapphire laser, you tend to make this sort of spectrum and this type of pulse.
I answered the question that on the right-hand side, the blue, that is actually multiple pulses.
Exactly.
Is that right?
Yes.
I just, the pulse length and, so train length are the same thing?
Yes. No, well, okay. Fourier transform. So forget about the laser and just talk about the harmonics for a minute. So forget about what laser we use and we'll just pretend we can buy whatever laser we like. And then just look at this supercontinuum and that pulse. If that's a 3 attosecond pulse, we know you need a kV bandwidth. So it's the uncertainty principle.
Right.
If this is a train of pulses and you take a Fourier transform, you get a picket fence of harmonics. And it turns out, even though this might integrate to be, if you look at all of them together, they might last 10 femtoseconds. It's not a 10 femtosecond pulse. It's not a Gaussian pulse. It's a picket fence. And it turns out if you do photo emission, it'll happen from one of these bursts. And it turns out, I'll show you how in the next few slides, how you can actually measure single attosecond lifetimes of in electron-electron scattering. But it's counterintuitive because previously people thought if you wanted to measure a shorter and shorter lifetime process, you had to make the pulse shorter and shorter. But that does not work if you want to probe a band-specific lifetime, which is often what you really want to look at, you know. So I'm hoping when I come to a concrete example that this will be a little clearer. Okay, we can talk more then. Okay, so we can make all this sort of shaped light, and we need to be able to make it and use it in the right way to measure something that, you know, that's interesting. And just showing you, we can make all kinds of light, you know, these pulses, you can make single pulses, you can make, you know, all kinds of light. Okay, so we're going to use angle resolved photo emission, time and angle resolved photo emission. So the idea here is we're going to excite a material and then use the EUV light to gather the photoelectrons. And the nice thing about angle resolved photo emission is you get a momentum resolved, momentum, time, and energy resolved dynamic map of the band structure of a material. And I'll say more about this in a little while. And the wonderful thing about using high harmonics is that we can make these relatively higher energy photons so we can probe the entire Brillouin zone, which is important because sometimes you see the signature of the different low energy excited states, you know, they're not at the zone center. And so you need to be able to look at the full band structure to see what's going on. We can also use magneto-optic spectroscopies. The wonderful thing, even though I won't talk about them, but the nice thing about using EUV light is that we get element-specific probes. We don't probe the L edges, the 2P, for example, in nickel, for example. We probe the M edges. They're still quite deeply bound at 60 EV. So that means in an alloy or in a multilayer, we can probe element resolved spin dynamics. Did you have a question? Yeah. Yes.
What is, I understand edges are the transition, but what
Yes.
is L and M?
L is for example, in nickel would be from 2P to the Fermi level.
Okay.
And then M is from the 3P to the Fermi level. So the splitting is not as large at the M edges, but we can still see if, for example, if I have an iron rhodium alloy or a Heusler alloy, we can still look at the magnetic state on each element of the alloy. So if we're doing things like, you know, doing do spin transfer, we can see that happening very well. Visible light probes the average magnetic state, so it's harder to see. It's very useful in a single element case, but in a multi-element case, this is one of the things we get. Now, I will forget about that for a moment because I'll do that better. Okay, so how do we measure attosecond lifetimes? So the synchrotron community have known about very short lifetime states for a long time. In the photoelectric effect, in photo emission, if we take 100 EV photon and we shine it on a material, in this case, copper, and this was work done by Eberhard at DESI, I think. And if you have 100 EV photon, what you expect to see in your photoelectron spectrum is pretty much a map of the band structure. So it doesn't really matter too much if you change, if the photon energy is 100 EV or 125 EV or 150 EV, you still expect to see a map of the occupied bands. Would everybody agree with that? Yeah, good. Now the synchrotron folks knew that sometimes you had to be more careful because what they see at certain incident photon energies, they would see these excited, and because they change with photon energies, they knew these were real unoccupied excited states well above the Fermi level. So there, you know, there's no we all know that there's low energy excited states. Of course, there's also high energy excited states. And as we talked before, since they're high energy, the lifetime can be very short. And in fact, you could tell that from their bandwidth. That 4 EV excited state. So now tell me from the uncertainty principle, what lifetime would that state have? Yeah. Thank you. Quarter femtosecond. Yes. Yes. And in fact, they're all over the place. Those excited states are all over the place. Here's a plot of the line width as a function of the final state energy. And you can see they can be enormous, 10 or 15 EV. So these are very short-lived real states, in the continuum. And they're very short. So this was a great, thing to try to develop the measurement capability, because we knew where the state was. We could reach the photon energy and we could develop a technique. Okay, so what's the technique? So we're going to use the high harmonics, and we're going to use the fact that I have a comb. Remember we talked about that we wanted a comb because we wanted to be able to select transitions and bands. And to be able to do this well, we wanted to look at 2 transitions, one from an occupied state into the unoccupied excited state. So that's an unoccupied bulk excited state with a very short lifetime. And then another into a free electron final state. And by comparing the 2 then, we could see if we could measure that lifetime, which we expected to be around a quarter. So everyone okay so far? Good. And we knew, like we talked before, we want to be able to look at certain transitions. We knew this was the excited state we were trying to reach. And we knew that, the transition probability was different for S and P polarization. So it also let us make sure we knew what we were looking at, that we could, in other words, we could see the final state with P polarization shown in blue, but not with S polarization shown in red. So we sort of knew what we were looking at. So we could photo emit into that excited state in the bulk, but there's no time resolution here. We're pretty much doing the same thing as Eberhard did with the DESI synchrotron. All right. So how are we going to measure how long the electron stays in this state before it makes it out of the material? And for that, and keep this ability to select which final state, so we couldn't just use a very broad band with light, what we do is we're going to use an interferometric technique. So we're going to also, as well as shining the attosecond pulse train on the material, we're also going to shine a laser beam. And it turns out in photo emission, if there's 2 types of photons present, there's a finite probability, in fact, a large probability that the photoelectron can absorb a can absorb the EUV photon and a laser photon. But in this path, the photoelectron absorbs an X-ray photon and emits an EUV absorbs an EUV photon and emits a laser photon. So there's 2 quantum interfering pathways to get to the same place. And if the lifetime of this state is different from this state, there's going to be a time delay when you look at the interference pattern. Does that make sense? So we call this laser-assisted photo emission, and take advantage of quantum interfering pathways so we can see if these different final states have different lifetimes.
Hit the sample at the same time.
At the same time, absolutely. And just use the fact that the on as well as the absorb.
Control their relative delay, like
Exactly. That's exactly what you do. You control their relative delay and you get this. So this is an interference pattern where you can see and this is plotting the delay between a free electron final state and the excited state in the bulk with the 200 attosecond lifetime. And you can see for these final states, they're all free electron, but suddenly you get this the shift because we're actually plotting the difference between the excited state in the bulk and the free electron state. And so that essentially measures the lifetime of the excited state. And so if you plot that phase delay as a function of harmonic order, or this is the same as photon energy, sure enough, you get this 200 attosecond shift. And because we can control an interferometer and we can stabilize it with a Heine or a diode laser, we can control the time delay very precisely. So it's a way to get very high energy resolution at the same time as getting high time resolution. Yes?
Is this relying on some assumption about like the line shape of the lifetime? Like it's like it'll just like some simple Lorentzian thing in order to get this interference?
Yes, but actually it's a direct measurement of the time delay. So there's a little bit, but actually this is a direct measurement in time. Is that right? So we're not taking the resonance width and doing a Fourier transform. We're not doing that. That slope is because we're referencing it to a free electron final state and the particular resonance position. That's what's being plotted here.
Yeah, I'm very ignorant about.
No, you're not at all.
So the color
Yes,
is what is plot?
the intensity.
The intensity
Yeah.
of those interference.
Yes,
So
exactly.
between the original light and then coming out of.
Yes, okay. Okay, so you're asking me why are we seeing modulations? Thank you. Anybody hazard a guess? And there's a hint. What is the time difference between the modulations? It's a half cycle of the laser pulse. Because of course, your field is changing. Now, right, as you change, your attosecond field is much higher frequency, but the attosecond bursts come out only every 1 1/4 femtoseconds. So of course you will get a bursts as you delay a long field with respect to a short field. You will get the laser assisted photo emission only in the time period that the harmonics are emitted.
Right. So, but that means that's actually that intensity is like both like initial or original light and like coming from the sample together is.
Yes. So it's absolutely. So what it's showing is essentially it's plotting all these photoelectrons, and the ones where we have an interference between a free electron final state and a resonant and a delay will show a slope here because some of the electrons are coming, they're stuck for a while in the real excited state and they come later. And that's why there's a slope on those, yes.
Where do rabbits come into this?
Rabbits, okay, so our field is terrible for acronyms. So like we measure light pulses with frogs, which are frequency resolved optical gating, and rabbits are reconstruction of something or other by interfering quantum pathways. I forget exactly yes. So that's where the rabbits came, yes. And there's, but I am saving you the explanation of all the acronyms because, it's better to just know the concept. Yeah. So everyone sort of happy that, if an electron comes out through a free electron final state, it's going to come out instantaneously, almost instantaneously. We have to be careful with instantaneously in our field, but almost instantaneously. But if it gets stuck for 200 attoseconds in an excited state in the bulk, there will be a delay. The population can build up there. So you see, that's why you get more photo emission from those states because the electron is held there for a while, so it doesn't scatter. Yes,
Have such a like accurate delay
yes.
calculation. How
Yes.
do you achieve that?
Oh, you interferometrically stabilize an interferometer
Oh,
with another reference kidney or something, or diode, yeah. Yeah. Now, this isn't so interesting, if you ask me, because you knew the line width, and okay, you could assume a certain Lorentzian or whatever, and you'd get something like this. So you're not really learning something new. So we went on then, so I mean, I just skip some of this and just say that our field is very famous for using attosecond pulses and measuring time delays, but if to be careful that you're just not measuring different conduction band sort of scattering lengths that just by way of how you did the excitation. In other words, it's easy to measure strong field physics effects. It's harder to measure like real intrinsic phenomena. So here I'll talk about measuring a real intrinsic phenomena. So we figured, okay, we did this first for nickel, and we could measure the lifetime of the excited state, and copper is very similar. So in copper, we could also measure the lifetime of the bulk excited state. But what was interesting is the free electron final states had very different lifetimes in copper versus nickel. Nickel, you can see it's very, very low, whereas copper had 100 attosecond free electron final state lifetime. We wondered, well, why would they be so different? Of course, the resonant line widths are different. So that's to do with, you know, the band structure copper versus nickel, or the excited state band structure in copper versus nickel. But this was interesting because it was this was supposedly a free electron final state. And the 100 attosecond difference meant it was all electronic. It had to be, there's nothing else can contribute in 100 attosecond to 100 attosecond time difference. And so basically, there's only two things it could be. It either had to be a difference, you know, move around. So either you expect the screening should increase the lifetime and scattering should decrease the lifetime. So either there had to be more electron scattering in nickel, more screening in nickel, or and then we realized that nickel has an unfilled D band, and that unfilled D band means that there's more phase space for scattering in nickel, and that might be able to explain this difference. And so essentially this is the picture that when the photoelectron is trying to leave in nickel because the band is not filled, there's a lot of states that it can scatter into due to interaction with so it could promote an electron up, whereas in copper the D band is full. Yes.
So since it's a free electron state,
Yes.
are you actually, when you measure the lifetime of that,
Mm-hmm.
are you actually measuring the properties of, say, a state that it's recombining into when it's recaptured by the material, or is that the wrong interpretation?
The interpretation is you know, it's making a transition, and it can make a transition to a free electron final state or this real state, excited state in the bulk.
And this is the time delay between these two.
On these two here, so that's of course up here. Here, these are both going into we're away from resonance, so we're just looking at what is the lifetime of free electron states in copper versus nickel. So no resonance, away from all the resonances. Yeah. So yes, photo emission is a multi-step process. First, you know, the electron is in the material and it gets excited. Then it has to make its way to the surface and get out. Yes. So it's multi. It has to get out for us to measure it. It has to get out for us to measure it. So we're measuring what gets out. And the yield is higher for these states because they're trapped, so they can't go off and scatter and, get trapped in the bulk. Sorry, I am talking about a lot of different. Is a multi-step process. Yes. Because the electron is only moving, is not moving super fast. So it does take a while to get out of the material.
So it's a free electron state.
Yes.
An electron that has enough energy that it could leave the bulk.
Exactly.
But it
I
still
go
has
back
to
here. I go
make
back.
it out.
What am I doing? I'm going forward instead of backwards. Sorry. Apologize. I'm going to go back here. I'm going to just go back here just to make sure that you can see. So this is the band structure. So this is the fill band. There's the Fermi level. Where our initial states are here. We use polarization to select which transitions we're looking at. And these are excited states 22 eV up in the band, normally unoccupied. But there's all these other free electron states that are not plotted here because there's no reason to. And photo emission, you excite the electron either into a free electron final state or into one of these final state resonances, sometimes people call them, but they are essentially just unoccupied excited states. Does that help a little bit?
I guess, are you measuring the emitted electron, or are you measuring emitted photons from transition?
Electrons. We're measuring the electrons, seeing how the and seeing at okay. So now let me go here. I know this is so these are the photons, and then we measure the photoelectrons, and so you expect bands, and you expect these interferences in between the bands, and all of them will oscillate because these EUV bursts only happen every 1.25 femtoseconds. So now let me go here. Thank you for these questions. So now you see the bands, the side bands are in between, and the side bands have this slope because we're referencing a free electron sideband to a real estate sideband.
And these free electrons have a lifetime because it's above the work function, but it's still inside the material.
Still inside the material, exactly.
Until it leaves.
Until it leaves, exactly. It's, but it's real. In the real state, just in instances. Yeah, exactly. Thank you.
So I also have a related question. So I'm trying to understand the role of the delay. So is it that you are exciting an electron, but not quite enough to like make it escape the materials? So you get to the bulk final band, and then the second pulse hits, and for some lower energy, it's able to get the electron to escape from that final band?
Nope. So, but thank you for the question. So, so we've got photo emission into this bulk final band, and then the electron will escape, or photo emission into a free electron final state, and then the electron will escape. We see both types of electrons. So we see electrons here, these are all above the resonance. So these correspond to electrons emitted into free electron final states. They'll be, for this harmonic, it's this one. For the next harmonic, it would be up here. And that's what these are. These little things in between are the sidebands that correspond to the interference between two pathways. In this pathway, the photoelectron absorbed an UV photon and emitted an infrared photon. Along this pathway, the photoelectron absorbed this EUV harmonic and also absorbed an infrared. And it's like this because harmonics are spaced by two every odd order because they're dipole transition. So you have to absorb each harmonic corresponds to an odd order of infrared photons. And then we just delayed this laser field with respect to this field, and you see everything oscillate because these bursts happen every 1.25 femtoseconds. So there's EUV light around only during that time. So then when you look at this interference pattern, you're really just plotting what's coming out as a function of electron kinetic energy. And so these are all the main harmonic emission, the photoelectrons due to absorbing this number of harmonics. And then in between here are the sidebands corresponding to the two adjacent interfering quantum pathways.
Okay.
And there's a slope because you're beating a path through a free electron final state with a very short lifetime and a path through the excited state resonance with a long lifetime of 200 attoseconds. Did that?
Yeah.
Great. So it's just it's a way to measure a very specific lifetime with a band specificity. And we did the same then in copper, but the difference between the excited state lifetime in nickel versus copper, you know, it's interesting, but you know, it maybe not. You know, it's really just the band structure is different in nickel versus copper. But what was interesting here, we thought, is that the free electron states in copper versus nickel had a different lifetime. And so because electron us look at these electron scattering processes in copper versus nickel.
I have a
Yes,
without this kind of your tool would never be absorbed.
exactly.
Yeah.
Nobody might care, but people do care, and I'll try and get to where I.
This kind of difference can kind of macroscopic property of conductive property of the copper.
I'm going to try and get to that now, Minhei. Exactly. So what we yes. So what is it useful for? Exactly. So we asked that question. So what does being able to measure 100 attosecond time delay in electron scattering in copper versus nickel do for you? For anything got to do with the material property. So what it allows us to do is measure what's called the electron correlation matrix. So what's the likelihood of scattering as the photoelectron is trying to get out, which is what we were talking about. That the photoelectron absorbs either the EUV photon or an EUV plus or minus an infrared photon, and then tries to get out. And so if you're able to measure this in copper and nickel, does it tell you anything about the ground state properties? Minhei rightly asked. The first thing we did was try to figure out what was the anomaly. Was the anomaly nickel or copper? And so when some simple free electron gas models, you find that the anomaly is nickel, that copper can be explained by relatively straightforward free electron gas models that are referenced here. So it was nickel is the anomaly. And so then what we did was yes.
So this is like a 30 plus EV electron state. That's not a free. It's not a free state.
It is a free state.
It is
Yeah,
a free
yeah,
state, but it just can't
yeah.
be explained by free electron gas.
Yes, it can
Yeah,
be.
yeah.
Yes. Yeah. Because it's very high energy. Exactly.
Yeah.
Yes, and I will get to the Fermi level. Okay, we are making our way there. I guarantee you. And so yes. So what we can do is fit our free electron lifetime and quantify what is this electron interaction matrix, electron interaction matrix. So we can measure that now for copper and nickel. But as you exactly and rightly said, these are all very high energy electrons. Nobody cares about them except synchrotron people or EV. Now, we'll compare the measurements done with 2-photon photoemission that can measure the lifetime near the Fermi level. And in what you can see is in copper, the same Coulomb interaction matrix works all the way from the Fermi level, all the way up to 40 eV. So that, whereas in nickel, you have to have a much lower Coulomb interaction matrix to explain the 2-photon photoemission versus the high energy. And so what we can do then is say, where is electron screening happening in nickel and how big an effect it is. And I think this graph I like, because do you notice we go in EV from the Fermi level up to 40 EV, and look at the lifetimes. They go from about 1 attosecond to a picosecond. So it's like 6 orders. Yes, Andre. Yes. Yeah. Oh, just, you know, in this is, we're not heating the electrons. So in all cases, you know, I mean, in a imprecise way, so forgive me, because I know, you know, but all states below the Fermi level are full and all states above the Fermi level are empty.
Is the difference, is the lowest E minus AF that you measure?
Yes.
Is the difference E minus AF larger than AF or smaller than AF?
These are all our measurements. These are all our measurements. Yeah, and this is 2-photon photoemission data.
Is it scattering really from the states which are really close to the
Oh,
level?
yes, so
Or the differences of the order of
yeah. So down here, the differences are much less than the Fermi energy. Exactly. And so what is, you know, what we were saying is the ability to measure electron scattering and figure out what the Coulomb interaction matrix is can let you say, you know, what screening is near the Fermi level. If you compare, you have to compare it with 2-photon measurements. But otherwise they measure that and they don't know what this is. You don't really know what M should be. Now you could guess that it should be like copper. So, you know, you could say something, but here on the graph, we were able to say, well, this is quantitatively where the screening is. And of course, it's exactly the question you asked, Andre. Look, it only goes up to about 2.5 or 3 EV. That makes total sense, isn't that right? Because that's the kind of, you know, energy scale you expect screening to be happening on. Okay.
Photo emission here.
We didn't do it. This is data we took from the literature. A whole bunch of groups do this. So this is well, so we put data from lots of different measurements. Yeah.
Yeah, like why 2-photon photo?
Oh, because they were measuring the lifetimes near the Fermi level. So then we could see if the Coulomb interaction matrix was the same. Here it's 0.6 is what they measured. We measured 1.8, but that would be the 1.8 line. So we know the difference here has to be screening because they measure a longer lifetime. See, we would predict the lifetime should still be sub-femtosecond if only electron scattering was happening. Does that make sense? But they measure much longer. Copper with Coulomb interaction matrix of 1.4, you get very long, you get very, you know, there's the photoelectron lifetimes are long. You know, it's a filled D band, so of course there isn't, your density of states is much, the density of states for scattering is lower. So it makes sense. So, yeah. Anyway, so I agree. I give this as an example because it shows how you would make an attosecond measurement. We never made one again after that. So, and the reason is, of course, we wanted to answer the questions like are being answered, you know, in this school. So how do you see charges and spins and phonons and many-body interactions talking to each other? So that's what I'm going to talk about for the next half an hour. Now, our field of ultrafast science had a very simplistic initial view because a lot of the initial excitations were done in metals, which, and if you don't ask anything below, say, 100 femtoseconds, your very simple kind of phenomenological theories would work, that the electron bath has a very low heat capacity, that the electrons, say, for example, in gold, are what's going to absorb the light. So you expect, if you irradiate, let's say, gold with a femtosecond laser, you expect that the electron temperature will shoot up. Then there'll be collisions with phonons. Phonons have very small, low energies, 100 millielectron volts and less, and so the lattice will heat up very slowly, in taking a couple of picoseconds, and eventually the electrons and lattice will have the same temperature. And that is, understood for many, many years. But of course, as you might expect, this does not apply when you're looking at a strongly coupled material, because you don't get to separate the electron. And the scattering is not incoherent, especially on short time scales, because the way intuitively I think about it in my head is if you have charges coupled to, for example, a strong amplitude breathing mode, then those are the phonons you're going to excite when you excite the electron bath. So what you're going to have is a very sort of interesting state where the electrons are excited and the strongly coupled photons are excited. But the rest of the phonon bath doesn't really participate for a while. So it's an interesting range to look at these quantum materials. So, and it turns out that if you have a phase transition during that excitation, there is no reason for that electron temperature to behave monotonically. In fact, you should see jumps and all kinds of stuff as the heat capacity changes depending on the coupling. And in fact, we can see that. Okay, so you know all this. So, and this is just for the experimentalists. What in our field, part of the confusion was that everybody would do the experiment differently. Everybody had their own laser, it had a different pulse duration, they did their experiment at a different excitation fluence. And so it turns out people would get different, let's say, decay constants. They would try to rationalize it. And of course, in reality, everybody was doing a different experiment, because depending on how much energy you put into the system, you might or might not drive the phase transition. So for a long time, they would have these arguments that were great because nobody knew the answers. You could get very excited. But of course, all that was happening was that everybody was doing a different experiment. But now we know what we have to do. You have to look at everything, and you have to do the experiments as a function of fluence, laser fluence, so you actually can sort of see, what are you exciting? Who's talking to who? And then, of course, do theory. And so we're going to use pump probe photoemission now. So a little bit from what we talked about with the lifetime. Here we will, yes? Sure. This, believe it or not, this is, we have data on this. If you have one of these tantalum diselenide that has a strong amplitude Star of David lattice distortion, that if you excite the charges, because it's a Star of David lattice distortion, you know that the the occupied states for the electrons must be screening those ions. And then you know that the excited states should be delocalized. So if you excite that material with a femtosecond laser and delocalize the charges, you will start an amplitude breathing mode. That's an isentropic system for a very short time, because only that the charges and the breathing mode are coupled. So essentially, the distribution has to modulate, and the distribution mean the Fermi level, so the temperature is modulating with the but it's not an energy flow, it's a distribution that, yeah, you have to keep a constant entropy for.
What excitation energy?
Just a Thai sapphire laser, yeah, very gentle excitation. And so what we'll do is weak laser pump and then harmonic probe so we can get the full band structure, and then we look at the gap, and we take line outs across the Fermi level to see the distribution. Everyone okay on that? Okay, and I just wanted to acknowledge this, that there's some beautiful work done, of course, New Geddick, and this is work from Kiel, Kaya Rosnichols, and Michael Bauer, and you know, it's just a lot of work in this area now, and Dan is going to be talking about it too. So we, our community, this is work of Kai Rosnichol and Michael Bauer. We had this idea back early on when harmonic-based ARPES were just being explored, that if we looked at some of these beautiful 2D materials that might be Mott or excitonic or pyrals, that because electron hopping happens faster than buildup of screening, which is faster than strongly coupled phonon mode, they all give rise to a gap. But surely if we took a laser and drove it through the phase transition, that we might be able to tell what the ground state order was just by looking at that melting time. It was something, you know, it was a proposal. We have papers published on this. But we realized in retrospect that that is really not a very good hypothesis, because if you drive it through the phase transition, you're not in the ground state anymore. So you're measuring, it's going to, in many cases, it will be laser fluence dependent, how much energy you put into the system. So that response time is not really an intrinsic property of the material. Yes. So then we got a little bit better. So we just got using far more gentle excitation and trying to look at the very low energy excited states. Because the low energy excited states are characteristic of the ground state. You know, they, by definition, right? And so I'll tell you about this, where we can look at mode selective electron coupling. I won't talk about this other things just because of time, and I don't want to run too fast. So you know, thanks for your question earlier. So we're going to look at this charge density wave material with the Star of David distortion. We'll come in with the laser pulse, and we know that in the ground state, when we're in a ground state order, we know that the occupied orbitals must be screening the ions, or the lattice couldn't distort into that ground state. And similarly, then we know that the excited state, they must be delocalized. And it turns out that because the amplitude mode is mostly in plane, if you excite this material, then you sort of can, for a while, you actually have a more monolayer type material. And so it turns out that the heat capacity, because the coupling between layers, those phonons are not excited, there's no way to take laser light and channel it to those phonons very quickly. It turns out that the heat capacity in the material drops by a third, because essentially you've decoupled the top layer from the other layers. But yes.
So these little states through a resonant process?
No.
Okay.
No, just look at their nature. But before that, I wanted to just talk about this. If we excite the amplitude mode, you know, so it's breathing, so you know the band structure has to be moving, all right? And it turns out the Fermi level also has to be smearing because it's an isentropic system. So the blue shows the band shift. So this is gently exciting the material. You shift the band a bit and it rings. It rings with the frequency of the amplitude mode. And if you take a line out across the Fermi level, the temperature also goes up and down. These are not small changes in temperature. This is electron temperature in 1,000 degrees Kelvin. So these are very large oscillations, but it's not oscillations in energy. It's just changing the distribution. Does that make sense? Because those electrons are only talking to the strongly coupled breathing mode. And so that's what we're going to use. I'm not going to go through this a lot other than to show you that this is the line out across the Fermi level. This is temperatures in degrees Kelvin, and you can see it go from cold to medium to hot, back to medium, back to hot. You can see the Fermi level, the Fermi smearing, but not exactly due to temperature, but due to, electronic entropy. And then I'll go to the more interesting case. Talk about this too much. Okay, this is a more interesting case because it's trying to use this capability. We can look at the electron temperature or let's say the Fermi distribution more accurately, to try and figure out in two different 1D materials, what was the nature of the ground state. Okay. So we're going to look at this RMO, rubidium, blue bronze, and TSI. Both of them had been proposed to have a gap based on polaron interactions. And what I'll show you is that turned out to be not true in either case. And I think people at this summer school know very well that 1D materials are very interesting because the electrons cannot avoid each other. So they're stuck, they're stuck interacting. They can't do anything about it. And in 1D materials, you could have interactions based on Peierls distortions or polaron, which are a real space, a distortion coupled with a charge distortion, or a quantum liquid based on a Luttinger liquid. And so all of those types of ground state orders would be allowed. And in the quantum liquid, there's just very strong electron interaction. The collective excitations correspond to how distribution function is different from a gap. Sometimes in an electron spectrum, it's sort of hard to know if you have a polaron or a charge density wave or a Luttinger liquid type gap. It depends on the quality of the data and what you can look at. Okay, so let's look at this material first. And we lucked out that just when we were studying this TSI material, Steve Kivelson's group did a theory paper that predicted this sort of phase space for this type of material, that it should be a charge density wave insulator. This is just a general class of materials. If you have strong electron phonon coupling, if you heat it up, it would go to a bipolaron insulator. And if you heat it up still further, you would have a single polar. And excited state should be that you should have, if you measure excitation, you should see the gap melt, and you would see a dispersive free electron band and a flat band corresponding to the different polaron states. So we had something with which we could compare our data. And we were very lucky that when we compared what we were seeing in experiment here and taking the second derivative so we could see very small changes, that we had really good agreement with we could see the free electron bands and the single polaron bands and see that very nicely in comparison with theory. So that allowed us to assign TSI to be a bipolaron insulator, and RMO, we looked at, so we went back to something simple. The data here, this is sort of the definitive way we can assign a bipolaron ground state, but we could still measure the appearance and disappearance time of these in-gap states. Yes.
What temperature are you doing these measurements at?
This was 80 Kelvin here. Yeah. So we were, we were not, the whole point is, okay, is you don't melt the order. You barely excite the material to the point where you can barely see the in-gap excited states.
I just meant that, like the theoretical phase diagram said that as you cool it further.
80, yes. Okay, both of them were at 80 Kelvin. Yeah.
Did you?
Can we go? Can we make it colder?
Yeah.
We could.
The transition to the CDW insulator.
Yes, and we didn't here because we were more focused here on just identifying the ground state order at this temperature. Yep. It's if you go very cold, it's very hard to do the laser excitation, right? Because then you can put even less energy in and still maintain the ground state order.
With the electron temperature heating up upon burst.
So what you do is you keep turning down your laser fluence so that you're barely populating the in-gap states and you can barely see them. So you do not want to melt the order. In fact, you can see here, we don't melt the order. All we're doing is populating. So this is before pump, after pump experiment. You see this? So we're really not changing the dispersion of the band. We're just putting electrons into these low energy excited states here. And you can see the same with theory.
So is this like the fluence is like?
Exactly. It's so low. So before, what we used to do, I mean, this is the whole community. You would melt the order and look at the time scale for the phase transition, but that's not really telling you what interactions are sort of supporting the ground state. So this is a better protocol if you can do it. You just barely excite the material to barely see the in-gap states. You do not melt the order, but you barely try to populate the low energy excited states. And this is just showing then the characteristic single polaron and dispersive states that agree really well with the bipolaron ground state. Now we did also do the old approach of looking at the time, the response time, and sure enough, in this TSI material that we now have assigned to a bipolar bound state, sure enough, it has a very slow rise time for the in-gap states and a very slow decay time, which is what you expect if it's a lattice distortion. For this other material, RMO, it had a super, this is in blue, super fast population and decay of the in-gap states. So immediately we knew this is not, it had been postulated to be a polaron ground state. We knew immediately cannot possibly be true. But this was not definitive. We could say it responds too fast to be a, it didn't tell us, well, can you really definitively say what it is? So for that, then we did, we thought it had to be a Luttinger liquid, and then we did the experiment. So what do we know about Luttinger liquids? So this paper still has not been submitted for publication. So if you know anything about them, including Martin, help me as we if you have questions, because we don't have the full story, but we have some very neat data. So, but we know a Luttinger liquid with very strong electron-electron interactions. There's a power law distribution near the Fermi level instead of the usual you know, let's say near zero temperature occupation up to the Fermi level, and then, you know, a Fermi-Dirac distribution. This is most definitely not a Fermi-Dirac distribution. As would be here at zero temperature. Now, this is the old story I told you about as to what we expect, let's say, gold to do if we excite gold with a fast laser pulse. Let's say it was gold at room temperature, so we've got Fermi-Dirac distribution. We excite electrons to above the Fermi level. After maybe 20 femtoseconds, they've established a hot Fermi-Dirac distribution. Then collisions with phonons over a picosecond or so will allow the material to cool. So after about 10 picoseconds, we're back where we started. Everybody happy with that? Good. And your liquid. So start with our Latinger distribution. Then we excite the electrons, and we can measure that there's a hot Latinger distribution established within 90 femtoseconds, and every covered about 10 times faster than in a Fermi metal. And not only that, but we can measure the Latinger exponent alpha and the electron distribution oscillate with this characteristic frequency. I'll show you data next. That's characteristic of, let's say, a collective plasmon excitation. It's not the single plasmon excitation that would be the lowest. Because that's really, really small, low energy excitation. We can't measure that. But it's a collective oscillation of the plasmon oscillation of the electrons in the Latinger metal. So let me show you the data. Yes.
Are these different stations?
Yes. Yes. So this one is in LMO. Excuse me. Yeah. Yes. RMO, we looked at it, but the material quality wasn't good enough. And both of these are very similar. So they're both expected to exhibit Latinger behavior. LMO is known. Here, the interesting thing is that we can see a signature of Latinger behavior in an extremely fast excitation and cooling, and also see it, not the low energy plasmon, but at least a collective plasmon. Yep. Yep. Yes. Sorry.
So if you excite the Luttinger liquid,
Yes.
having some conceptual trouble with. Okay, so it gains some energy, but then somehow it loses energy to its side.
Yes, exactly. That is kind of what we were trying to wrap our head around. So how do you think about this? And like I said, we haven't the paper submitted, so it's still kind of things we're talking with Rahul and other people to try to understand how do we think about it. I'll tell you how I think about it, and I don't know if it's right. So you've got your electrons in the Latinger liquid characterized by your Latinger exponent alpha. If you take some of these and put them up here, you will definitely excite a plasmon, because you have reduced the distribution here. You've put them up here. We see a drop in alpha, which is what you would expect, because you've taken electrons out of the Latinger band and put them into excited states that are not, they can't see each other, so the alpha has to drop. But they cool pretty quickly back into the Latinger band, but now you've done something to a Latinger band that you could never do by putting the material on a hot plate. You've removed some of the electrons quickly and then put them back in. And of course, that's going to excite a plasmon because it's a 1D strongly coupled system. And that plasmon is modulating the band structure. So you have to, and we can see that because it modulates the Latinger exponent. We can see it in the data too. has to modulate the electron temperature the same way the breathing mode, when it modulates the band position, has to modulate the electron distribution, because you have to conserve electronic entropy. And the electrons are not talking to anything else. So they're only talking to themselves. Because you could never get it to cool in far less than a picosecond. So it's the excitation of the collective plasmon in the Luttinger electron bath that allows it to cool.
Okay.
But there's got to be dissipation somewhere, and I don't know where. But it's not phonons.
Too much using ARPES.
Yes, and I'll show you the data now. Yes, but I had to show you the picture first, because so this is the same sort of thing, started at 80 Kelvin, before the pump. This is after the pump. There's our electrons in the excited state. We wait for 90 femtoseconds because we have to wait for the electrons that are excited into a different band to go back to the Luttinger band. Then this is just a fit to show that we fit a Luttinger really. This is a really good Luttinger liquid for all the regimes we explore. It's a really good fit. And the data, if you take this, do the fits as a function of time and this fit, you have to fit both alpha and the electron temperature. So these are fits to the Luttinger distribution, but the fit and the data, there's little circle. See that is the data, and there's a line on top. So the experiment and the theory agree really well. So the fit is really good. Yes.
What?
Yes.
It extends to like maybe half an electron volt.
Yes.
Did you do the fit up to all those energy scales?
You only want to fit here because the distribution is, you'll have more confidence in extracting alpha and T at the Fermi level, because that's where the band is most Luttinger-like.
Because there's gonna be like some sort of strong covariance on those two parameters, I would expect.
Yes, and I have a whole pile of backup slides where we vary and see how much we could fool ourselves, and so that's why we know our.
Okay.
Yes, that's it. That was something we had to really convince ourselves of, exactly. And so here it is the data that's extracted from the fit to the Luttinger distribution. So this is where the laser is. You can see the minute the laser hits the material, alpha drops, because of course you're taking electrons out of the Luttinger band, so of course alpha has to drop. But then, as soon as the laser pulse stops, the electrons can start relaxing back into the Luttinger band from the excited states, so alpha recovers super quick. But because you instantaneously moved out some electrons and then put them back in, you also excite, of course, your electronic entropy has to be conserved, and you also excite a plasmon that also modulates the band structure a little bit because there's charges sloshing around. And I want to acknowledge Rahul, Umang, and Oscar for theory, and Anya, Na, Martin, Shunye, Tika, and Richa on the experiment. So I like to call this the quantum jello. So it's like when you have jello in a container. So I think about the electrons as jello. They're in the lattice, but they don't see the lattice in a Luttinger liquid. And so if you poke the jello, it'll vibrate itself and not really care about the container. So I don't know if that's a good analogy or not.
We can see.
This is the
frequency
frequency corresponding to the electron density in the Luttinger band.
Okay, so
Yeah,
it's like
if it were a plasmon.
like, okay.
Yeah, but it's not the low energy excitation, which is like a two electron,
Right.
it's a collective plasmon of the whole density in the Luttinger band. Sorry?
Is alpha the logical?
Alpha is the Luttinger parameter. Yes, so I can show you the little cartoon again. Oh, what am I doing? I'm going the wrong direction. Yes, so this is sort of to contrast what we understand, if we excited gold, that you would put all the energy into the electrons and then undergo slow loss of the lattice and then recovers in 10 picoseconds. So this is that old understanding from 1974, whereas in a Luttinger liquid, the electrons are talking to each other so strongly that the response time of the electrons is very fast. You decrease alpha very quickly, then the electrons relax from excited states back into the Luttinger band, but that, you know, taking electrons out of a strongly coupled electronic system, of course, will launch a collective plasmon in that whole distribution. And so you get ringing in both the Luttinger exponent and the electron temperature, and the cooling is 10 times faster than a Fermi metal. Because that,
45 femtosecond, you have the change in slope.
at 45 femtoseconds,
Slope oscillate?
yes, exactly. Exactly. And so I just show you the data. So this is a fit,
To the power law.
fit to the power, exactly, near the Fermi level.
So there, the electron temperature is also part of the fit to getting
Yes.
out the ARPA?
Yes, yep. But it's not really the electron temperature, but it's the electron distribution, because the system is isentropic because the electrons are not talking to anything else. So if you move them around and they relax back, you will have to see a change in distribution, because if you, and which is a change in temperature, but not really due to energy flow, but rather constant electronic entropy. So if you move the band, you're going to have to change the distribution. You have to. Because when you pull the electrons out, okay, I have a little thing here. Oh, there, sorry. When you pull, so this is sort of a more detailed version. So you got your Luttinger band. The optical excitation will put these up in a non-Luttinger band very quickly. That's the 45 femtoseconds. But then they relax back very quickly, so you have a hot Luttinger band within 90 femtoseconds. But that process of pulling charge in and then jumping it back launches the plasmon corresponding to the electron density in that band.
I mean, what's strange is you don't have to change alpha to talk about plasmon oscillation.
Yes, but the low energy, that's not the same as the low energy plasmon. That's the elementary excitation in the Luttinger. This is a collective plasmon involving all the electrons in the Luttinger band.
But do you ever see oscillations in conventional, three-dimensional?
Yes. That's why I showed I showed data showing that in a charge density wave material, because if you excite the breathing mode, it also makes the electronic bands oscillate. You also see oscillations in the electron distribution or temperature, if you want to call it that. And the only reason we were able to see it is that as we turned down the optical excitation and our ARPES data got better because we averaged more, we could suddenly see things that probably were there in other people's data too, but they just didn't know to look. Yeah. Sure.
Plasmon, so you said it was launched within half of the period of the plasmon?
Yes, yes.
So it's real frequency you can determine.
Yeah, and it does correspond to the expected plasmon at the electron density that's present in the Luttinger band.
Okay. And it seems like it's a easily measurable frequency.
Exactly.
Okay.
Yes, you would have to know to look for it. And you'd have to be yeah. So we're sensitive because we're looking at the band. We see the whole band.
Okay.
Okay. So the question is, see, we fit to this at the Fermi level. So we see the whole band and then fit alpha and T. So the question is, how would you, yeah, it's what would you look for? There must be some signature. There must be something modulating.
Yeah.
Yes.
Yeah. I'm just wondering because you said the period is, I guess the full period is 200 femtoseconds.
Yeah.
This is like,
yeah.
I just checked, I don't know this, but it's like somewhere around like 100 to 200 wave numbers.
Yes.
So if there's some sort of symmetry, you could figure out if it's odd or even, then plug it into infrared.
Plug it in. Yeah. I think
Yeah.
I have it somewhere. No, sorry, wrong. Yeah, I can't remember. Yeah. Yeah, we have a good Fourier transform, because and the interesting thing is it makes sense, their phase and time lag matters because, when you modulate the band, then it takes a while for the electrons to redistribute into the band. So we think that 20 femtosecond time lag, it corresponds to how long it takes the electrons to populate the band. Andre, am I BSing completely or does this sound reasonable? Sure. No. Yeah, yep.
What parameter of oxygen liquid?
Probably maybe the fluence, how many of the electrons we move, so how strong a kick, I'm guessing. So you want to, we need to excite it enough that we can see the oscillations, but not too much that we would like raise the temperature too much. Exactly, because see, to launch the plasmons, we have to, the optical excitation goes up into a non-Luttinger band, and then they have to cool back, and it's that process that I think launches the plasmon. So the frequency, I forget it, whether it's 6.6 terahertz, Martin, is that right? I think it's around that. Oh, no, it's here. Yes, no. Is it 6.6 terahertz? Is that right? Good. No, as the person who took this data, it was very hard to take because it takes a lot of averaging. And so something like that, and it does correspond to the expected plasmon that, in a 1D material in a Luttinger like. So as I said, we're still finishing up the paper with Rahul and Umang and others. Yeah. Good. So I think maybe with that we're sort of out of time. So I'll just thank you for your attention and again highlight the people who two of them are here, Na and is Richa. I just don't want to miss anybody, but Na is here, who is the first author and lead experimentalist on this. And thank you so much for your attention and appreciate the questions. Sure.
You have something to say the frequency. What physics sets the frequency of oscillation? Like, is it some intraband thing, or is it with it purely single Luttinger liquid plasmon frequency? Like density?
Yeah, that's what we think. Yep. Yeah, a collective plasmon. Yep. Yep, the collective plasmon frequency. Yes.
A log K dispersion. But it could be a whole bunch of couple, basically 1D Luttinger liquid that'll make jam, like 3D plasma.
Well, I think this is a 1D plasmon, a 1D collective plasmon.
But then it's the opposite.
So this is not the very low energy plasmon corresponding to a 2 excitation in a Luttinger liquid. This is not that.
But this,
So this is the whole density in the Luttinger band. That is.
There's some collective.
Yeah. Yeah.
But
but not the lowest energy plasmon excited, which are 2 particle excitations in a Luttinger material. That's not this.
Wouldn't expect it.
So there must be some wave vector that's picked out, some light scale that's picking out.
Yeah. So Umang is not able to calculate that. Because you can't, that there's so according to their theory, you can predict that there's a collective excitation, you just can't predict the frequency.
but isn't RMO is actually some quark crystal that you're shining light, or is that some fabricated, like really truly what the physical dimension wise?
So RMO,
Is
so she's is asking about RMO. It is well to by a lot of static ARPES measurements. So people know it is a Luttinger liquid, even though it's bulk, got these chains for the bands, specific bands. It's not every band, but at the Fermi level, it's well fit to a Luttinger distribution.
Yeah, when the
I'm
system,
not sure I could answer.
when the system initially loses energy, then it gains back the energy. The delta T is positive, so.
So I don't think it gains energy. I think what we're seeing, and I don't think it's energy. It's bands moving. Yeah, it's yes. So you're right. To a first approximation, we move electrons around with the laser. Alpha drops because we took them out of. They heat up because we put laser energy in, and then they cool super fast. That's the first approximation. Then because we moved electrons out of the Luttinger band, we excite this collective plasmon, and they're only talking to each other. And that seems to be the mechanism for the very fast cooling.
Yeah, when it cools, then again it goes up.
But that's just because we move electrons out of the plasmon, and the plasmon is modulating the band. So the band is modulating. As a result, the bandwidth has to change because you have to keep your electronic entropy constant. Whenever you move, you're going to have to change the. So it's not energy moving around as much as the band going up and changing distribution and down. At least that's our best understanding. So W and the amplitude mode breathing, the same things happen, exactly the same thing, but it's just a different collective excitation in the modulation. And I'm sorry we don't have a better explanation.
So yeah, just to make sure I understand. So you mean the oscillation part is due to the plasma mode?
Yep. Yep.
So then in normal form liquid, do you still see this? Because in normal form liquid, you still have non-zero plasma.
Yes, but we don't see, but they're not, if there's no strong coupling, the only reason you get that modulation by the plasmon is that there's very strong coupling. And so we see it in CDW materials, we see it in Luttinger materials. So whenever there's strong coupling, that the traditional way of thinking, you put energy into the electron bath and then it goes to the phonons, just does not work because other things can happen because there's collective interactions. So it just means things are coupled. Yeah. So the band, the lattice position in the amplitude mode, and that's why you can, when you modulate the band, you modulate the distribution.
Oh, sorry, I still have a question. So do you still expect that into the non-form liquid systems, you still observe that?
We do. I mean, we see it in that tantalum diselenide. We can see it in many materials, isn't that right now? Yeah, yeah.
Have the Fermi energy, like, because if you're shifting edge, but
I'm going to